Hello, this is TheoryStation, and I'm John Duggan. We're in a program now that I'm calling Principles of Math, and the series is just basic ideas. I just want to talk about basic ideas that we use in mathematical modeling, some logic, some math. This is the first installment of the series, and I actually thought I would start talking about mathematical modeling in general. From my perspective, anyway. I'm a specialist in modeling of politics and economics, and bargaining and elections, and most of the models I do are game theoretic. But mathematical modeling is a much bigger enterprise. I think that my comments will translate to other types of modeling. I should also say that I'm not a philosopher of science. I'm not trying to be very deep here. It's just how I think about it. And maybe it'll be interesting to other people to think this way. So to begin, what is a mathematical model? Well, what is a model? There's all kinds of different models, right? We talk about model cars or model airplanes. So models can be physical things made of plastic or metal or wood. And what are they? Well, they're simplifications of something that's bigger and more complicated. And a mathematical model is sort of the same thing, except it's made from mathematical parts. So it's a simplification or representation of something in reality that's too complicated for us to think about directly, so we translate it to this representation where we can apply formal methods to think about it in a very precise way. So I like to draw pictures, and I'll just kind of draw a schematic of how I think about modeling here. So to begin with, there's something in reality that's very complicated and messy, so I'll draw it like a blob. And there's something happening there, okay? There's some processes that lead to some outcomes. These initial conditions we can call antecedents or initial conditions. And then those lead to some outcomes. Again, that process is, usually very complicated and probably beyond human comprehension to understand in full detail. So what we do is we come up with some representation of this, and this is the mathematical model, and I'm going to draw that as just a nice, instead of a messy blob, just a nice box. And so this is a simplification or representation of whatever's going on in the world, right? So let's indicate that with this arrow pointing down. That's the representation arrow. This mathematical model, it's, again, not made of metal or plastic, but things like sets and functions and relations and things made up of those things. That's probably not very clear right now, but those are the building blocks of a mathematical model. In contrast to the kind of messy, complicated stuff in reality, the mathematical parts, they fit together in very precise ways, and there's a certain rigidity and cleanness and precision to those things. I should say that this representation arrow is it's a little bit mysterious in the sense that there's no set toolbox that allows you to do that. It's really, when you write down a model, you're trying to simplify reality, but you want to keep all the essential features there. And how do you guarantee that you do that? Well, there really isn't a guarantee. We like to think that that we're able to do that, but that just comes with experience. You have to use your judgment, and there's some art to that arrow. I will say that a lot of times you find out that arrow didn't do what you thought. The model wasn't good enough, and you go back and you revisit the model and you improve it. So this is actually an iterative process sometimes. And anyway, once you have this mathematical model, then you can apply formal analysis to this. And those are the tools that we have from logic and math. This is an enormous toolbox, but in mathematics, you've probably heard of or had a calculus course. That's a great set of tools. There's real analysis and linear algebra, and the list goes on. There's a huge set of tools at our disposal. I like to think that I use a lot of them, but really, as a fraction of the whole universe of tools, it's probably very small. So we apply these methods of formal analysis, and we apply those to the model, and then that gives us some results or conclusions. And these are in the form of theorems or maybe testable hypotheses. Or if you're doing more complicated work, maybe a structural, you're working with a structural model and you get a distribution over, a probability distribution over observables that you can use to estimate parameters. Anyway, there's lots of things you can do with a model, but the idea is we apply formal analysis to get those results. And in contrast to the representation arrow, this formal analysis arrow, there's no, if you do it correctly and your arguments are rigorous and you follow all the rules, there is no judgment about that. If you do it right, your results will follow from the assumptions in your model, and that arrow is really unquestionable. Now, there's still an art to it because you can derive results in ways that are more efficient or more beautiful or elegant. But it's very different in that if you do everything correctly, you don't go back and realize, oh, this arrow doesn't give me what I thought. Once we have these results, then they'll have some implications for reality, for these outcomes, and ideally this whole thing commutes. That is, if we follow these arrows, if we write down our model, apply formal tools, and then draw implications, then we see some correspondence with reality. I haven't said much about what that implications arrow is. Partly that's because it depends on how you're using the model. And I should just mention right now, there's a couple different ways that you can use a model. And I'll just put these terms out here to begin with. So one use of a model is positive. It's positive analysis means that you're using the model to predict outcomes. So the model would then be predictive The implications then would be predictions for what we should see in the real world. That could mean a natural experiment, or it could mean a laboratory experiment, but predictions of things that we're actually going to see. Another use of the model is normative. Normative analysis, instead of being predictive, is prescriptive. It's trying to say what should happen instead of what will happen. And then these implications would not be predictions for what we would see. They would be saying, well, this is what should happen. One thing that, if you haven't thought about this stuff before, one thing that should occur to you right now is, but wait, isn't that a subjective matter? What should happen? And the answer is yes. So in that normative approach, you actually have to say explicitly what you mean by should. And you can do that by writing down an objective function, and then we want to maximize that objective function. So it could be, a firm maximizing profits, or an agency maximizing benefit minus cost, or there could be some measure of efficiency. We want to maximize that measure of efficiency. A different approach is axiomatic, where we write down axioms that should be satisfied, and then this arrow here, this implication arrow, is then telling us what those axioms imply. I know that's abstract right now, but much later on we'll be talking about that stuff in more detail. So that's my schematic for mathematical modeling. I'll just end by adding one thing, which is here we're just talking about mathematical representations and some different ways of using those mathematical models. There are, of course, non-mathematical ways of representing reality, and we do that all the time when we're talking about the world. We have sort of normal language that we use that represents reality. We have art and music and poetry, and so we can represent reality in other ways as well. So if I were going to be a little bit more exhaustive with this schematic, I would draw maybe a bigger blob down here, which would include not just models made up of math, but models made up of words and paintings and melodies. And so, what did we say? Language, art, music, poetry. But those representations, again, are kind of squishy and imprecise, at least very different from the mathematical ones that we're going to be talking about. So I'm going to draw that as a big red blob. And those representations give us something. But they don't give us these kinds of predictions or prescriptions that we get from mathematical modeling. But they give us beauty, they give us intuition, which all serve a purpose, and those are there. But we're going to be focusing on these bottom three arrows here, and that's it. That's just in a nutshell how I think about mathematical modeling. So the rest of this series is just going to be just throwing out some very basic ideas that we use in this kind of analysis, and then we'll go on from there.